So I'll wind up this one, and then we will introduce the chapter 20. Okay, so let's see. We did the ZSEF products, and I explained, if you've forgotten, we were doing the Regius selectivity and stereo selectivity, the ZSEF products. That's what we did. That's what I'm scrolling through right now. The anti-coplanar rule, where we are going for the beta hydrogen that's 180 degrees orientation to compared to the leaving group. So that most of these were giving us the ZSEF products where possible. So for today, we'll do the Hofmann products as we wind up this chapter 10, which is technically a review, and then we will introduce the aromatic compounds, chapter 20.
This chapter 20 on the test?
I sent the email. I said exam 3 will be everything that was not tested on chapter 2 moving forward. So if you are covering it, yes, then it's gonna be there, including the Monday. That Monday is gonna be Monday 27. The contents that will be taught on Monday 27 is examinable for exam 3. Okay, so anything between the time you did exam 2 and Monday 27th evening will be tested. Okay, so now let's see. I think this is a slide right here. Okay, so Hofmann implies the less substituted double bond turning out to be the major. That's what Hofmann elimination means. And to get Hofmann product with E2, you have to use a bulky base, because the bulky base is not going to go within the molecule looking for the most, looking for the beta hydrogen sitting on the most substituted carbon. It's going to go for the most available beta hydrogen. So I would start by showing my beta hydrogens as usual. Okay. I want it to be anti-coplanar, so I'm gonna just show those are the candidates. You realize this is a methyl, this one here is also a methyl, so whichever one you take is the same thing, but this is the other type of the beta hydrogen. So now if you're using bulky bases, turns out the ZSEF product will be of less yield. As you can see, the ZSEF product from this reaction has less percentage yield. Reason being, these two guys are bulky, meaning they're huge, meaning they're sterically hindered. Now the Hofmann product turns out to be the major, formed in higher yields. Higher unexpected yields, because one will always think for the more substituted carbon. But let's look what's happening. If you have a base, the base can take out a beta hydrogen sitting on a more substituted carbon compared to the other carbons. And if you do that, you would get this product right here. That will easily happen if the base is small. Okay, small sized. You will get the ZSEF product as the major 71% according to this actual experiment. Now the small base might forget and take out one of these hydrogens, so let's pretend that the small base is taking out this hydrogen. This is how you'll push your arrow, like that, and then of course this leaves. That will give you the Hofmann product. But the Hofmann product with a small base is less favored. So if you want the least substituted double bond to be formed, then you have to use a bulky base. Now I'm going to remind you, this is tri-substituted alkene. Remember the Zaitsev rule, in reactions where you're making double bonds, the alkene product that is more substituted will be favored. So this is Zaitsev product when using small base. Tri-substituted, because I have a carbon there, I have a carbon there, I have a carbon there, bonded directly to the double bond that's circled. So it's tri-substituted. Here you have two hydrogens here. So this is a carbon, that's a carbon, so this is di-substituted. It's less substituted than that, that's why it's called Hofmann. Now, the Hofmann product will tend to be in high yield if you're using a bulky base. Obviously, you see this is this is a huge structure. Those are metals. Here you have the ethers. This is even bulkier than this one. This is a butoxide, whatever this is, 1, 2, 3, 4, 5, 6, 7, heptoxide. 1, 2, 3, 4, 5, 6, 7, heptoxide, tert. Heptoxide. This is tert. Butoxide. There are 4 carbons, 1, 2, 3, 4, but. It's an alkoxide, so butoxide. Here you have 7 carbons, 1, 2, 3, 4, 5, 6, 7. So it's 7 heptoxide. Alright, so that's the Hofmann elimination, where the least substituted product is favored because you're using bulky bases. So the bulky base, if you choose to take this butoxide, let me modify this, you'll take out that. So this is bulky. So if it's bulky, it's not gonna go within the molecule looking for this guy. It's gonna take what's outside. So it goes here, takes out the hydrogen, make a double bond, this leaves. It's still E2. That's how you make the Hofmann product in greater yields. Because this one is bulky, the molecule is secondary, it's tertiary actually. The beta hydrogens that would have given the Zaitsev product is hindered within the structure, so the bulky one, the bulky base does not have easy access to take out that hydrogen to give you the more substituted alkene. Do you have a question on that part before we do examples? Okay. So let's see. So again, your bulky base will take out the most accessible hydrogen to make a double bond as the leaving group leaves. Of course, this is a transition state. It's easier to do that than here where the metals will hinder it from approaching to take out the other hydrogen sitting on a secondary carbon. You know, this hydrogen right here is sitting on a secondary carbon. This hydrogen right there is sitting on a primary carbon because the carbon is bonded to one other carbon. This carbon is bonded to 2 other carbons. So the bulky base will take out a hydrogen that's less hindered, sitting on a less substituted carbon, less substituted beta carbon. So the transition state here is just explaining if you want to take out the hydrogen sitting on the secondary carbon, there's going to be some hindrance by the alkyl groups nearby. So you have 2 of them here. Here you only have 1 hindrance. So you'd rather go with this transition state, and that gives you the Hofmann product, which turns out to be the major because there's less energy barrier. The Zaitsev would be the minor. Okay, so if you need to find the reagent that you'd use to produce the desired alkene, one would first ask him or herself questions. This is one of the options of the beta hydrogen. This is the other option of the beta hydrogen. I'm looking at my product. I'm seeing it looks like this guy was taken out and a double bond was made. Turns out this is primary or mono. I think, let me use, this is mono substituted. If you take out that, now if the base would have taken out this beta hydrogen, okay, the product will look like this. You have a carbon, a carbon, a carbon. This is tri-substituted. Because it's tri-substituted, it's more substituted than this. One would have thought this is a Zaitsev product. Zaitsev product. This one will be the Hofmann product because it's less substituted. Which means you have to choose a base that's not going to go in there. A base that goes in there must be small because it might fit into the pocket within the structure. Small, strong base can do that. Because you're taking out the outer one, we need a large. See, the product is giving you the Hofmann, so you need a large, that is called bulky base. So we look at our choices. Which reagent would you use to produce the desired alkene? Someone tell me.
3.
I agree. Now I'm gonna ask the same person who answered. What is the role of this?
Is that the solvent?
Yeah, this is just playing the role of a solvent. So I would ignore the metals. So the metals, so I'll know I have a negative charge on the oxygen. Okay, and then I have 3 ethers, so I'll go 1, 2, 3. That's what this 3 means. This CH2 is this carbon. This CH3 is this carbon. Repeat that 3 times connected to the carbon in the middle. You get this structure. So this is bulky. Okay, this one is not bulky. In fact, this one will do E1, and I told you E1 always gives the Zaitsev product. This one, okay, this is weak. I need to say that. This is a weak base and small. So that should give you E1 product and should give you Zaitsev. This one right here is CH3O negative. That one is small base, strong base, but it's small. So this should have given you the Zaitsev, which is this. This would have been the major if you used choice 2. Again, the methanol right here just plays the role of a solvent. So I agree. The answer is 3.
Would you expect any of the solvents to play a part in the reaction?
The solvent will play a part in, let me see.
Like, would it produce any minor product?
Yeah, minor products will be produced here, and in that case it's going to be SN1 minor product. That's why in this case one would want to use much of the base. Of course, the base cannot outrun, the volume of the base cannot outrun the volume of the solvent. Then the solvent will not play the role of a solvent. But yes, you're right. You'll see minor products. And in this case, in fact, we're choosing choice 3. SN1 is not possible because still the solvent is bulky. So most likely you're just going to see this guy alone, because the solvent is bulky, which means it's not going to play the role of a nucleophile. If it has to do anything, it will play the role of a base because it's bulky. And if it plays the role of a base, it can't go in there, so it still has a choice to take out that. So I don't expect minus in this case. According to the reaction shown, I don't expect any minus. It's just going to be E2 by itself. Okay, so what's the answer to this one? Identify the major and minor products formed in the reaction. So I see a CH3 right here. So I'm going to give my hydrogen some stereochemistry. just to follow up what we learned last class, anti-coplanar rule. So this is the hydrogen to be taken out because it's away from the chlorine, and still you have other beta hydrogens. So you have that, and you have this. Of course, there are two of them. I see that my base is bulky, so it should go for this hydrogen because it's sitting on a primary carbon. These two hydrogens are sitting on secondary, which means they are more hindered. So the bulky base will go for the one that's most accessible, which is that. And then make a double bond on this metal bond. This leaves. That's how you get that, which will be the major. You have these hydrogens on the secondary carbon, so it's possible to take those out. If you do that, either you take out this hydrogen, which is anti-coplanar to the leaving group, or take out this. Notice that the molecule is symmetrical. Whichever one you take out, right, you're gonna make this product. So the minor will be 1. Any question on that? Okay, I think the Hofmann elimination then is clear. Let's introduce this aromaticity. Sorry about that. Let's say discard. Okay, so we'll use the rest of the time to discuss this. I'll let you know when it's enough discussion for it. Okay, and let's see, when is today? When is today? 23rd, okay. So aromatic compounds, aromatic, that comes from the word aroma. I'll caution you, though these mushrooms look so cute, don't try cook them. Most of these mushrooms that are colored, they are very, very poisonous. In fact, you eat it, it's one way to your grave. Most of them, they are so toxic that you're not going to have enough time drinking an antidote. So it's important whenever you're buying mushrooms, make sure you buy the right species. Anyway, apart from nutrition, let's talk about this cute looking mushroom. You see the purple color. That color is due to aromatic compound that's within the natural product, which is the mushroom. That's not the only thing. I think you also see leaves. You see some leaves. It's because of chlorophyll. Chlorophyll contains a ring called apophorine. I'll show you how apophorine looks like. So it gives you that color. And you see other colors here, like the orange things here. All these colors you are seeing is because of conjugation and aromaticity from the grass, the leaves, the mushroom. Now, one other thing that's common to you, I think it's your blood. Your blood is colored because it contains, of course, the heme. We call it a protestic group of the protein. The heme also is made of porphyrin. The same similar porphyrin that makes chlorophyll is a similar structure, has a similar structure to your heme, the protestic group of your heme. It's aromaticity that brings about these colors, which also is tied to what we call conjugation, the pi sigma 6 system. So we're going to be looking at 4 specific rules that help us to determine whether a molecule is aromatic or not. Okay, so the benzene is the oldest known organic molecule, one of the oldest known organic molecules, and is linked to cancer cases like leukemia. And of course, it's a controlled substance. The scientists who discovered or who first examined or researched the structure of benzene, chemical formula and structure of benzene, is Friedrich Kekel. He proposed the structure of the benzene way before you were a cell, 1865. And he discovered that there's a 6-membered ring. It's a 6-membered ring with 6 pi electrons. But he failed to say the bond he failed to determine the bond length. So some other scientists in the 1900s, I think 2 or 3 scientists came by and won Nobel Prize explaining the bond distance, the bond angles, and all that. Anyway, today we know that it's aromatic. All these bonds of the benzene have equal length. Why? Because these pi bonds are not drawn fixed on the ring. They keep on going round and round and round and round. So we should as well even just draw a circle in the ring, because we can't even tell where the pi bonds are. They are resonating. That makes the bond length between that of a single bond and a double bond, because it's a hybrid. So benzene is highly conjugated, and it's a ring. Those are first two rules that you need to know for finding aromaticity. Okay, so nomenclature. Fluorobenzene, there's a fluorine on the benzene. Nitrobenzene, there's a nitro, this is a nitro on the benzene. And then ethylbenzene, there's an ethyl, the benzene. This is supposed to be methylbenzene, but it's very commonly called toluene, the common name. This is supposed to be hydroxybenzene. This is a hydroxyl group, but we call it phenol. This is supposed to be called amino, that's amino group, aminobenzene, but we call it aniline. Easily call it aniline. This is an acetyl group. It's a ketone, so we call acetophenone. Of course, now this one will be benzophenone. This whole part. Benzo. Okay, the benzene is here. This is the benzo part, and this part is the phenone. Okay, benzophenone. And benzoic acid, for those who took or are taking Chem 261 or will take Chem 263, sorry, C-Lab 263. The first experiment you'll work on is reacting benzoic acid with a base. So that's benzoic acid, and then this is methoxybenzene, but we just simply call it anisole. And then of course that's a sulfonic acid part. That's an aldehyde, so we call this benzaldehyde. And then we use styrene to make styrofoam, which I doubt we will do because we lost some classes. I doubt we'll do the last chapter, whatever chapter it is, I think 27. Okay, so that's styrene. Alright, so let's do next slide. Before you answer this question, I'm going to explain something. So sometimes your benzene is substituted. Okay, so I'm going to call this a substituent. Let me call it reference substituent. So you already have a group on the ring, and then you do a reaction and put the incoming group here. So let's say there's another group here. So that was your reference. So if you have a group on this carbon right here, it's gonna be called ortho. So for example, let's say I have this structure. Remember in your slide we called this toluene. We called it toluene. So your toluene has a Cl here. So the name will be, because the Cl is next door to your reference group, the methyl group is your reference, comes from the parent name toluene, so that's why it's our reference. This chlorine is ortho, next door, O-R-T-H-O. Okay, it's ortho. So the name here will be ortho chlorotoluene. Orthochlorotoluene. Otherwise, okay, my pen is not wanting to write there. Otherwise, you just write it as O chlorotoluene. So let's use the same toluene as an example. You know, toluene is the smell that you smell in paints or in your shoe, whatever you call it, or that shoe paste thing that you apply on your shoe brush, shoe polish. So if the chlorine is right here, this position right here, one carbon after this reference substituent, is called meta. So if the chlorine is there, then we're gonna call this molecule meta or meta-chlorotoluene. The meta part can be abbreviated with a name. I can't write in italics. If you're typing, it has to be italicized. So, and let's do one more position. So notice that you have two orthos and two metas. So this other side is equally an ortho. Okay, this side here is equally a meta. So if the chlorine is on the opposite, directly opposite to your reference group, which this is our reference group because the parent name is toluene, if the chlorine is there, this position is called para. So the name will be para-chlorotoluene. Okay, so this position right there, that position there is para. Para, we use a P. That's the para position. Otherwise, just write it as P chlorotoluene. So now, which pair of names are equivalent? Find the answer.
B.
B. Okay, we will flow from the top and see why B is the answer. So notice that the toluene is just this. Your reference group again is the CH3. So meta-fluoro, it means fluorine is there. And then here, it means our fluorine is down here. So that's not the answer. B, I have a phenol and the bromine is on the second carbon, so that's ortho. Notice that this is a reference carbon, so it's 1, 2. Okay, so B is the answer. The next one, para-nitrobenzaldehyde. So our reference this time is benzaldehyde, is the aldehyde. Para means the fourth carbon over. 1, 2, 3, 4. Nitro is NO2. Comparing that to the 3, they are not the same. That's out. And then you have aniline is where you have NH2 as your reference group. It's on meta position. The chlorine's on meta position. Here you have the aniline with the chlorine. In fact, this does not exist. There's no, if you put here chlorine, that carbon has too many. You have excess bonds. So it's not even a thing. So this is out. Okay, so yeah, the answer is B. Is someone having a doubt and a question on that slide? No question? Okay, so you see the series follows 1, 2, 1, 3.
Can you go back to the old slide?
Yes.
I just gotta finish writing down.
Okay.
Alright, I'm done. Thank you.
Okay. Okay, so this slide is just showing you the numbering systems. So where you have similar groups, pick one to be a reference, the other one will be a substituent group. But the main thing you want to know is whenever you have a mixture, always identify your parent ring. The way to know your parent ring is to know these common ones. I'm gonna mark the common parent rings: toluene, phenol, aniline. There's one more or two more: benzoic acid and anisole. Those are the major guys that will most likely gonna give you a parent name for this class, for the scope of this class. There are more, but obviously these are surveys, so I'm limiting myself to very few choices. I'm just giving you a test of each chapter as far as we can go. Okay, so if that's the parent, then this is your reference: 1, 2, 1, 3. No, the ring has 6 carbons. This will be 1, 4. Okay. Okay. I think that's done. Let's switch gears. Can someone tell me where do you know this one will be used? Someone? Don't tell me you don't know.
What's the question?
What is the use of 2,4,6-trinitrotoluene?
Is it a medicine?
No, that's a bomb. TNT? You see that in movies.
Oh,
You see it.
Would you mind going back to the previous slide just real quick?
Okay.
All right, thank you.
Okay. So here, this is not tested, but I'm just gonna describe it. Whenever you have pH on a long chain, like let's say you have pH here on a long chain, it's gonna be called a phenol because it's a substituent. Now, if you have a long carbon chain, and you have it like this, then you have an extra carbon between the phenol and the long chain, is gonna be called a benzyl group, just like you would say methyl, ethyl, propyl, isopropyl. So whenever it's taken as a substituent with an extra carbon, it's benzyl group. Whenever it's just pH to the longest chain on one end or in between, without the carbon in between, it's gonna be phenol. Okay, giving you a few seconds if you're writing. We are about to go over the rules on determining whether a compound is aromatic, anti-aromatic, or non-aromatic. Yeah, this is what I want. Don't worry about this slide. Don't worry about that. This is where we are. Aromaticity. Although benzene has pi bonds, it reacts differently compared to regular alkenes. If you were to do an addition reactions with regular alkene, for example, if you had this plus Br2, you'll add the two Brs across the double bond. That's how alkenes behave. They add across the double bond. Benzene has 3 double bonds. One would expect, okay, if I add the same Br2, which is X2, then I should add the 2 X's here, but it doesn't happen. Why? The reason is benzene is aromatic, while regular alkenes are not aromatic. And we're going to define aromaticity. From this point onwards, we're going to define aromaticity. So instead of benzene adding the 2 bromines, if you give it Br2, usually in presence of a catalyst, we won't get into the reactions. Instead of doing the X2 or the Br2 addition, it just takes 1 bromine and swaps the hydrogen with the bromine, with one of the bromines. So it undergoes substitution because you're swapping, you're switching groups. Here it's addition because you're losing the bond and adding your reagent onto the molecule. Here it's substitution. The hydrogen is no longer there. It's replaced by the electrophile, in this case Br. So this is one of the experiments that early scientists did to qualify molecules as aromatic, because they will react differently compared to other alkenes. But we are not going to go into those reactions. That will take like 2 classes to explain all those reactions. So again, regular alkene will do addition. See, the bromines are added across. You did not lose any hydrogen. The hydrogens are still there. Similarly here, and usually it's anti-addition, which means the bromines are added in opposite orientation. So same thing with the ring. Anti-addition. Bromine with the same reaction, no reaction. Of course, I told you if bromine has to react, you have to add a metal catalyst like iron tribromide. It won't react. No catalyst, it's not gonna react. Obviously, again, it's because benzene is aromatic. So if you are asked a question, why does benzene not react through addition reactions like other regular alkenes? The answer is benzene is aromatic. The regular normal alkenes are not aromatic. So those ones will undergo addition, benzene will undergo substitution. Okay. Benzene undergoes aromatic substitution and not addition reaction like regular alkenes do, because benzene is aromatic. Okay. So here comes the 4 rules. Not all cyclic systems are aromatic. Haeckel's rules will tell you when a compound could be aromatic using the following conditions, and all 4 must be met for a compound to be judged as aromatic or labeled aromatic. So rule number 1, it must be a ring. It must be cyclic. So it must be cyclic, which means it must be a ring. Each atom of the metal has an hybridized p orbital, which means it must be conjugated. Of course, let's draw the benzene ring here and see if it applies for if it follows rule A and B, rule 1 and 2. It's a ring, check. But do we have an hybridized p orbital? How do I even know that? We look at hybridization. So I have hydrogens. Can someone tell me what's the hybridization of all these carbons? Someone?
SP?
No, it's
SP2.
It's sp2. You have 3 electron domains. A double bond is 1 electron domain, so there are 3 of them. It has to be sp2. What is the molecular geometry of sp2? Hybridized carbon.
Trigonoplanar.
Yes, underline the word planar. You're gonna need it for rule number 3. See, I always tell you, you don't want to forget any information we learned before. So the rule number 3 says the unhybridized p orbitals must form continuous cycle, which means they must be conjugated around the ring. So the ring must be planar. Remember, I just asked you. It has to be planar. sp2 centers are usually flat on that area, but overall it must be flat on each and every corner of the ring. Some rings have sp2 hybridized carbons all around, but overall the ring is not planar. I'll show you that one when time comes. Rule number 4, the number of electrons. Okay, so benzene qualifies number 3. The number of electrons residing in the pi electron cloud, either the pi bonds, they form us. Let me see what this is saying. There's a typo somewhere, wrong grammar. Okay, the number of electrons residing in the pi electron cloud must be equal to 4n plus 2, where n is an integer. I don't know what this means, too much English for me. So I'm just continuing to read. The number of electrons residing in the pi electron cloud is equal to 4n plus 2, where n is solved to an integer or 0. So in other words, n must not solve for a fraction. That's what I want you to say, to write down. n must not solve for a fraction but can be 0. So n can be 0, 1 to infinity, but never a fraction. When you solve for n, it should never be a fraction. So what does that mean for rule number D, or rule 4? So for molecule to be aromatic, you must test it using the 4n plus 2 rule. So let's use our benzene here and say, okay, benzene, are you gonna follow the 4n plus 2 equals to number of pi electrons? Okay, and solve for n for a whole number. Are you gonna do that? So where we have to start here. Count the pi electrons. You have 3 pi bonds. Each bond is 2 electrons. Each pi bond is 2 electrons. So we have 6 pi electrons. That's the number we put on the left side of the equation. 2 is part of the expression. So we need to solve for n. That's how you use this rule D. You are solving for n. You'll always want to solve for n. If n turns out to be a fraction, that structure is not aromatic. It's something else. It might be anti-aromatic or non-aromatic. We'll define that soon. So 4n equals to 4. N will turn out to be 1. It's not a fraction. So benzene passes the 4th rule. Okay. So in summary, for a molecule to be aromatic, it must be a ring. Each atom of the ring must have an hybridized p orbital, and of course, if you have sp2, if you compare sp2 to sp3, you're missing one p. When we are talking about hybridization in whatever chapter it was, I told you that p will be upstairs without electrons. It's unhybridized. That's the p orbital that takes electrons that will do resonances. So it must be planar. Of course, sp2 centers are molecular shape trigonal planar. And then the last rule, number 4, which to me in my brain I usually consider it first. You use the 4n plus 2 equals to number of pi electrons. That's the equation. 4n plus 2 equals to number of pi electrons. I have 6 pi electrons, for example, in benzene. I put 6. 4n plus 2 equals to 6. N solves for 1, and benzene passes because n did not turn out to be a fraction. If it turns out to be a fraction, then we have to test another rule, which is 4n equals to number of pi electrons. That will be for the anti-aromatic compounds. So let's move on and build to that. So benzene is tested as a ring. Check. Is this a ring? Nope. Even though it has 6 pi electrons, sp2 carbons, it's not a ring. It's not to be considered. Next rule to summarize, benzene is completely conjugated, which means if I push this one here, this bond will be pushed here, and this will be pushed here, which means there's complete resonance. So which means it must be conjugated, because those bonds will end up relocating completely. This one is not conjugated because see, I cannot push this double bond here. There's no pi bond to give way. So this one is not conjugated because I cannot do complete resonances. So I'll say not fully conjugated. It's partially conjugated because I can push this one here and stop there. There's no way I can go further. As also, the other way to look at it is to check the hybridization. There are 2 hydrogens there. Okay, this carbon right here is sp3. Remember, sp3 is trigonal sp3 is tetrahedral, molecular shape, which means this molecule turns out not to be planar. And if it's not planar, then it's not conjugated. That's another way to look at it. You want at least sp2, either sp or sp2 on the ring, but not sp3. If you see sp3 anywhere on the ring, that molecule has to be non-aromatic because it's not planar. It's failing at least one of the first three rules. That's how you qualify non-aromatic. So that said, this one also has the same problem. That's an sp3 carbon center. While it's conjugated to the left, I cannot push this double bond here. There's no pi bond to give way to do resonances. So it's not completely, these are not completely conjugated. They are partially conjugated. This sp3 carbon breaks the conjugation. So again, this is not aromatic, but specifically we're going to label it as non-aromatic. Non-aromatic structures, they fail at least one of the first three rules. Those are non-aromatic structures. They at least fail one of them. It could be one or more. They might pass rule D, the fourth rule. Like if you look at this structure, it has 6 pi electrons, just like benzene. So it passes the fourth rule where N will solve for 1. But it fails the planarity rule. It fails the conjugated rule. So it fails those 2 of the first 3. So it's non-aromatic. So don't just say it's not aromatic. You have to say it's non-aromatic. Soon enough, we're going to define anti-aromatic. So there's aromatic structures, there is non-aromatic, and there's anti-aromatic. We are building into that. So the third rule, the ring must be planar. I told you you can use hybridization to tell if it's planar, because if the carbon centers are sp2 hybridized, they would be predicted to be trigonal planar. Now open your ears wide open. This structure right here has all sp2 carbons. All these carbons are sp2. So one would tell himself or herself, because all carbons are sp2s and all sp2s are trigonal planar, then this ring must be flat. It has been found that through chemical means, if you react this ring with bromine, it does addition reaction. So if it does addition reaction, then it's not a regular conjugated cyclic system. It's not it's not an irregular conjugated cyclic system. It's behaving like an alkene because it's doing addition reaction. That was chemical proof. The other proof was to crystallize it and make as crystals, do X-ray on the crystal. It was found that even though this structure has all carbon centers sp2 hybridized, so trigonal planar, it takes a shape of a tub, like your bathtub where you shower. So it's not planar. Because it's not planar, the right correct as label for this molecule is non-aromatic. Why? Because it is failing at least one of the ABC rules. It's not planar, it's not completely conjugated actually, because for conjugation to happen, the molecule must be planar. Okay? So now, what about this guy? To determine whether this molecule is aromatic, anti-aromatic, or non-aromatic, we have to use the fourth rule. Why? Because it's a ring. It passes rule number 1 because it's cyclic. Rule number 2, is it fully conjugated? The answer is yes, because if I push here, the arrow, this bond has to give way. It comes here. Notice that all the bonds moved around the ring. So it's completely conjugated. It's conjugated, and it's conjugated completely, not partially. And it's completely conjugated in this case because I see all carbons are sp2s, and of course it's small. It's not this exception. This is an exception that I told you. If you are looking at this, then you'll think that this guy is anti-aromatic, but we'll come to that. Let's define what anti-aromatic means. So it passes rule number 1, it passes rule number 2. Does it pass rule number 3? The answer is yes. It's planar because everything is sp2, and it's small ring, so I expect everything should be sp2, and the carbon should be planar on the surface. Rule number 4, will it pass 4n plus 2 rule? Nope. It's gonna fail. 4n plus 2 equals number of pi electrons. Let's prove that. How many pi electrons are in this ring? Someone tell me. Oh, it tells you 4 pi electrons. You have 2 pi bonds, so each bond 2 electrons, so 4 pi bonds. So let's try and test for this rule. 4n plus 2 equals number of pi electrons. So our pi electrons are 4. Let's solve for n. Remember, for a molecule to be aromatic, when you solve for n, it should never be a fraction. So it will be 4n equals to 4 minus 2. 4n equals to 2. Divide both sides by 4. N will be equal to 2 over all over 4. Turns out n is a half. That's how it fails rule number 4. Now, does it pass the 4n rule? Yes. Instead of passing the 4n plus 2 rule, it passes the 4n rule. Actually, the rule is 4n equals to number of pi electrons. In this case, 4n equals to 4. This is the rule for anti-aromatic compounds. So anti-aromatic compounds will pass rule number 1, rule number 2, rule number 3, but fail rule number 4, which is 4n plus 2, and instead pass 4n equals to number of pi electrons. So instead of passing this, it passes 4n equals to number of pi electrons. Number of pi electrons. So where the n solves for a whole number. So let's do it. So 4n equals number of pi electrons. How many pi electrons? 4. So we put 4 there. N is equals to 1. So it passes that. It passes the 4n rule, not 4n plus 2. So that's how you qualify anti-aromatic compounds. Remember, I defined non-aromatic as molecules which fails one or more of rule number 1, 2, and 3. So now I've explained how you determine if a compound is aromatic, anti-aromatic, or non-aromatic. So if I come back here, someone tell me how many pi electrons do we have on this guy? Pi electrons, someone?
8.
Yes, there are 4 pi bonds, which means 8 pi electrons. 8 is a multiple of 4. So this one, if you test it with 4n plus 2 equals to number of pi electrons, which means 4n plus 2 equals to 8 electrons. So 4n will be equal to n minus 2. 4n equals to 6. N equals to 6 all over 4. That's a fraction. So it fails the fourth rule. If you test it for 4n rule, 4n equals to 8 electrons, n will solve for 2. It will pass it. It's passing the fourth rule, but it's failing the planarity, right? It's a tab shape, so it's failing rule number 3. Where's my pen? So it's failing rule number 3, and in turn, because it fails planarity, it's gonna fail conjugation, because for structure to be conjugated, those sp2 carbons must be on the same surface and flat and planar. So a molecule that fails rule 3 will automatically fail rule 2. So to classify this compound, this structure, I'll classify it as non-aromatic, because like I said, non-aromatic structures will fail either rule 1, 2, or 3, or a combination of those. And
If it has sp2 orbitals, how is it not non-planar? Is it because of the addition reaction after the addition reaction?
yeah, it's because the way it behaves with the addition reaction, and it's because of its natural shape, which is tab shape. Like it was crystallized by a scientist and found that the crystal structure is that of a bathtub, which means it's not planar. And if it's not planar, look at the p orbitals. The p orbitals have to be parallel. Are they parallel? They are not. If they are not parallel, then they cannot throw electrons to the next p orbital. So complete resonance is impossible. So this is a structure that you should just memorize, so to speak, because looking at it, one would think it's anti-aromatic, because all over it's sp2. So one would think it's completely conjugated, because one would think that you can throw around these electrons, but it's not possible, because it turns out the ring is not flat. And in fact, tested by chemical means, it reacts just like other compounds. So that's why. There's another molecule that you need to know that's going to be non-aromatic, but it looks like it's aromatic. I'm forwarding. I want you to see the two exceptions. Okay, this one. So if you focus at this molecule, let's give it the test. It's a ring. Rule number 1 passed. Rule number 2. I can push these pi bonds all around. Like I push this gives way. So one would say it's conjugated. Okay, one would say it's conjugated. I'm going to put a star on there meanwhile. And then because it's all over, you'll see that it's sp2 hybridized. So one would say it's plain. I'm saying one would say because it turns out to be wrong. I put a star on that one. So let's go on number 4. 1, 2, 3, 4, 5. So I have 10 pi electrons. So if I test, of course 10 is not a multiple of 4, so I have no need to test with 4n rule. So I test with 4n plus 2 rule, which is 10. So n will solve for 2, so it will pass rule number 4. The reason why I marked these 2 is because naturally, looking at the molecule crystal, turns out that you have hydrogens in here. Can someone tell me what they see? What's the problem with the hydrogens right now, the way they are drawn?
Is it steric stream?
Yeah, so those hydrogens, instead of going inside the ring on the plane, because you're assuming the ring is planar, I marked it with an asterisk. Instead of them doing that, one will go axial up, the other one will go axial down. And by doing so, the ring puckers. So one side of the ring will go up, the other side of the ring will drop down. So it's no longer planar. So if it's no longer planar, then it's no longer completely conjugated, and then it's non-aromatic, because it turns out it's failing at least one of the first 3 rules. So this molecule on slide 18 is an exception. You have to memorize that. So one would have thought that it is aromatic because it passes 1 through 4, but turns out these 2 and 3, it fails. It turns out it fails. On first glance, you'll think it passes everything, but turns out it fails based on the crystal structure. So instead of it being aromatic, it's going to be not aromatic. We're not going to say it's not aromatic. We have to say it's non-aromatic. Because anything that's not aromatic could be non-aromatic or anti-aromatic. That's why I'm saying the correct word should be, the correct word is non-aromatic. Okay, so I think that's very clear. Now let's look at some few examples of aromatic compounds. So here you have a benzene, you see you have 1, 2, 3, 4, 5. So it's 10 pi electrons. N will solve for 2. This complete conjugation is cyclic. All carbon centers are sp2, so I expect this one to be aromatic. This one has 14 pi electrons. 4n plus 2 equals to 14. So N will solve for 3. It's cyclic. I can push these electrons all around It looks like a triple benzene, so it's aromatic. This is phenanthrene is an isomer of anthracene. It has 14 pi electrons again. So if this is aromatic, that should be aromatic. The compounds which have hydrogen and carbon only on their structures, and they have fused benzene, they are called benzenoids. I think you guys use, what do you call it? Do you call it mothballs? Mothballs are made of fused benzene rings. It's not a good idea to keep smelling those sweet smelling compounds, because with time they cause cancer of the blood. Just briefly expose yourself to them, or don't do it at all. So there's all resonance throughout the structures like illustrated down here. You can push those double bonds completely around and rearrange them. Okay, I'm gonna stop on this one for today. Next time we meet, we'll do tons of examples and practice the 4 rules of aromaticity, which is what's left off here. That's all that we'll do in the next class session, which I'll look at my calendar. It looks like, did someone check for me when is the last day of the class? I want to count the number of reviews possible after exam 3.
Do we meet on that Thursday before finals week?
Which is that day? That's what I'm seeing. Usually, that's my question.
It's either the 5th or the 7th. I'll check the website.
And did you happen to post last lecture video on Moodle? Because I didn't see it.
Yeah, I posted it.
Is it under chapter 9 or chapter 10? Because I know the chapter 10 was a review.
I thought it's chapter 10. If it's not showing, I'll come back and post it again. Because last week Moodle had issues. Let's see. Because I immediately posted it after the class. But I'll check it again and see if it did not go. Let's see. So remind me again, what did you say the last day?
The last day of class is Friday, May 8th.
So we have the May 7th.
And May 5th.
May 7th and May 5th.
Yeah, those are the 2 class days before our final.
Okay, then we'll use those 2 classes for the review. Which means for us, the last day I'm teaching you content is going to be on Monday.
And for the final, it's completely on everything we've been taught the whole semester?
Yes.
And will there be a review, like what pointed out, like what we need to know, because it's a lot of information?
There's no way, that's a difficult thing to do.
You said that we'll learn new information on Monday. Does that mean you're just going to send out like a video lecture that Monday? Because we usually meet Tuesday, Thursday.
Okay. No, we'll do I meant Tuesday. The last class will be on Tuesday.
The last class of new information, and then we'll review on Thursday?
What date is Thursday?
Thursday is May 7th.
Thursday
and
next week?
Next week is the 30th. We have a test that day.
Yeah, so that answers you.
Oh, okay. I thought you were still talking about the week before finals. So the last day of new information is the 28th?
Yes.
Tuesday?
Yes.
Okay.
Yes. And then after that, I think according to our calendar, it shows we have 2 more classes. We can use those for review.
Yeah.
Okay.
And then the information that we learn on Tuesday will also appear on the test?
Yes.
On Thursday?
Yes.
Okay.
I'll see if I get time, because I've been having internet issues. If I get time, I'll pre-record it ahead of time for those who want to clear it up. And then on Tuesday, we'll meet to do examples.